Take a breath. Now, hold that breath. Imagine holding it, not for a minute, not for an hour, but for 60 million years. That is roughly what a stretch of ocean once did, according to some of the rock now sitting under your feet or under someone's feet, somewhere near the equator. Sealed. No sky touching water, no wind touching wave. A world with a lid on it, and the lid was ice. Picture a geologist crouched on a hillside in Namibia, running a bare hand along an exposed rock face. Under his palm, two kinds of rock meet at a single seam, no transition, no in-between. Below the seam, diamictite, the jumbled, scraped-up debris a glacier leaves behind when it grinds its way across a landscape and dumps everything it was carrying. Above the seam, touching it directly, with nothing between them, a pale band of carbonate rock, the kind that only forms in warm, shallow tropical seas. Frozen planet, touching tropical ocean. At one seam, on one rock face, with no gap in between. That should not be possible. Not if you believe, as most people quietly do, that climate is a system that corrects itself, that if the planet tips too far toward ice, something always pulls it back before it goes too far. A thermostat, a planet-sized safety mechanism, always self-adjusting, because otherwise, how would we be here to notice? For 30 years, the mathematics said otherwise. The equations describing how ice reflects sunlight, worked out by a Soviet climatologist in 1969, contained no reverse gear. Past a certain point, they said, the ice doesn't stop. It doesn't level off. It runs away and it keeps running, and there is nothing in the model that brings it back. If that model is right, then somewhere in Earth's deep past, the planet took a swing at freezing itself completely, permanently, ice pole to pole, and by the physics understood at the time, it should still be frozen right now. We should not exist. Nothing should exist except the ice. Something broke that spell. And for 3 decades, nobody could agree on what it was, or whether the planet had even gone that far in the first place. I want to tell you about the ball of ice this planet may have become, the geologist who staked his career on proving it, the fight that followed him for the rest of his life, and the strange, almost accidental mechanism that may have thawed a frozen world using the very thing that seemed to be making it worse. Because if the freeze really happened the way some of this evidence suggests, then everything that came after, every animal, every one of your cells, this video, you watching it, traces back through a gap in a model that, for 30 years, had no way out written into it at all. The book that sent me down this rabbit hole is called Snowball Earth, the story of the great global catastrophe that spawned life as we know it, by a science writer named Gabrielle Walker. It's built like a detective story because that's what it actually was. A scientific mystery pieced together across continents and decades, centered on one geologist, Paul Hoffman, and a discovery in Namibia that either proved the planet had frozen solid or didn't, depending entirely on who you asked. I should say up front, I don't think every part of this case is closed. Some of what you're about to hear is about as solid as science gets, rocks you can put your hand on nearly every continent on Earth. Some of it is a model that works beautifully on a chalkboard and has never fully been reconciled with what the fossil record needed to survive. And some of it, including a study published in 2025, is actively reopening questions that geologists thought had been settled years ago. I'll flag which is which as we go, because that honesty is kind of the whole point of digging into a story like this one. But let's start at the beginning, because the beginning of this story is a man nobody believed. In 1949, an Australian geologist named Douglas Mawson looked at glacial deposits scattered across South Australia and made a claim that, on its face, sounded almost absurd. He proposed that Earth had once been globally glaciated, not just cold at the poles the way it is now, but frozen as a whole. Ice everywhere, not an ice age, an ice era. Nobody took it seriously for very long. It didn't fit. And then, within a few decades, plate tectonics came along and seemed to kill the idea for good, because plate tectonics gave everyone a much simpler explanation for cold rocks in strange places. The land had moved. What looked like tropical glaciation wasn't tropical at all. The continent carrying that rock had simply drifted up from the poles over hundreds of millions of years, then drifted back. No mystery, no global catastrophe, just geography playing tricks on the eye. For a while, that was that. Mawson's idea went quiet. But quiet isn't the same as gone. In 1964, a geologist at Cambridge named Brian Harland went back through the evidence with fresh eyes, and what he found was harder to explain away. Glacial deposits, the unmistakable signature of ice grinding across rock, turned up not just in one place, but on nearly every continent on Earth. And crucially, several of those deposits, once you accounted for plate movement as carefully as anyone could at the time, still landed close to the equator when the ice was there. Think about what that means for a second. Glaciers at the equator, not glaciers that used to be somewhere colder and drifted into the tropics afterward. Glaciers that were forming ice actively at latitudes where today you'd find coral reefs and rainforests. Harland didn't have an explanation. He just had the paradox laid out plainly. Cold climate rock in warm climate places all over the planet at apparently the same span of deep time. He stated it. He didn't solve it. And for the next few decades, it sat there, a strange, uncomfortable fact that didn't fit anyone's tidy picture of how a planet's climate is supposed to behave. Here's why it's uncomfortable, and I want you to actually sit with this, because I think it's the hinge the entire rest of this story turns on. You have probably absorbed, without ever being taught it directly, a kind of folk physics about climate, that it self-corrects, that Earth has knobs and dials that quietly keep everything within livable bounds, the way your body sweats when it's hot and shivers when it's cold. It's a comforting assumption. It's also mostly true. There really is a thermostat, and I'll get to how it works in a moment, but a thermostat is only a thermostat if it has a way to reverse itself. And in 1969, a Soviet climatologist named Mikhail Budiko sat down and actually did the math on the piece of that thermostat that involves ice, and what he found should unsettle you a little. Here's the mechanism, and it's simple enough that you already intuitively understand half of it. Ice is pale. Pale things reflect sunlight instead of absorbing it. Ocean and bare land are dark, relatively speaking, and dark things absorb sunlight and turn it into heat. So, more ice on the planet means more sunlight bounced straight back into space, which means a cooler planet, which means more ice. Picture a mirror that grows a little larger every single time it reflects a little more light. That's the loop. It doesn't stay balanced, it compounds. Budiko modeled what happens to that loop once ice creeps down past around 30 degrees latitude, roughly the line that, on today's Earth, runs through the southern United States or through the middle of the Sahara. Past that point in his model, the mirror wins. The growing ice reflects away enough sunlight to cool the planet further, which grows the ice further, which cools the planet further, on and on, with nothing in the equations that pulls it back. No floor, no reversal. Just a runaway slide, in his model, all the way to a fully ice-covered Earth. Sit with that for a second, because this is the part that turns a rock in Namibia into a genuine crisis for how we think about this planet's stability. If Budiko's model is a faithful description of how the physics actually behaves, then somewhere back in deep time, if Earth's ice ever crossed that 30-degree line, the planet shouldn't have been able to save itself. Not through any process contained in that model. It should have kept going. White, from pole to pole, forever, or at least until some outside force, something not in the ice albedo equation at all, arrived to break the spell. And Harland's rocks, glacial debris scattered across nearly every continent, some of it sitting stubbornly close to the equator, looked uncomfortably like a crime scene photo of exactly that. So now you have two separate discoveries, made by two different people, in two different decades, that don't seem to know about each other but fit together like a lock and a key. Harland found the fingerprints, Budiko found the motive, and the terrifying detail that whatever did this might not have a mechanism to undo it. Nobody put the pieces fully together yet. That took another scientist, working alone with an idea that sounded, at the time, like something out of science fiction. His name was Joseph Kirschvink, and in 1992, working at Caltech, he did something almost nobody else had thought to do. He took the paradox seriously enough to try to actually solve it rather than explain it away. Kirschvink went back to the ancient rocks with a tool that doesn't care about anyone's assumptions: paleomagnetism. Here's the idea, and it's genuinely elegant. When certain rocks form, tiny mineral grains inside them align themselves with Earth's magnetic field at that exact moment, like microscopic compasses freezing mid-swing. That alignment records the latitude the rock formed at, not perfectly, but well enough to check a story against. Lock that record in, and hundreds of millions of years later, you can go back and ask the rock, where were you really when you formed? Kirschvink checked the glacial deposits, and the compasses agreed with Harland. Ice near the equator. Not a fluke of a couple of odd samples, a pattern confirmed by physics that doesn't lie about geography. So Kirschvink did the thing that separates a curious observation from an actual theory. He gave the paradox a name, and he gave it a proposed ending. He called it Snowball Earth. And critically, he didn't just say the planet froze, he proposed how it might have gotten out again. His idea centered on volcanoes. Here's why that matters, and it's worth understanding the thermostat properly now, the one I mentioned a minute ago, because Kirschvink's escape hatch depends on breaking it. Under normal conditions, Earth has a genuine functioning long-term climate regulator, and it runs through weathering, rain and rock, slowly, chemically eating away at exposed stone. When rain falls on bare rock, it pulls carbon dioxide out of the air and locks it into minerals, then washes those minerals to the sea. More carbon dioxide in the air means a warmer planet, which means more rain, which means faster weathering, which pulls more carbon dioxide back out of the sky. Too cold, and the opposite happens. Weathering slows, carbon dioxide from volcanoes keeps trickling into the atmosphere unchecked, and the planet slowly warms back up. It's a thermostat with a lag of thousands of years instead of seconds, but a thermostat all the same. Warm world, faster weathering pulls the temperature back down. Cool world, slower weathering lets it climb back up. This is the mechanism, by the way, that keeps our actual present-day Earth from swinging as wildly as it otherwise might. And it's real, it's measured, it's about as settled as long-term climate science gets. But now imagine what happens to that thermostat if the ocean itself gets sealed under ice. Weathering needs rain hitting exposed rock and liquid water carrying the products of that reaction out to sea. Bury the whole planet's oceans and most of its land under kilometers of ice, and you don't just slow the thermostat down, you switch it off entirely. No rain on bare rock, no rivers carrying weathered minerals anywhere. The valve that's supposed to bleed off extra carbon dioxide freezes shut. But the volcanoes don't stop. That's Kirschvink's insight, and it's the moment this story stops being purely a disaster and starts being something stranger. Volcanoes under the Earth's crust don't care that the surface is a frozen wasteland. They keep erupting, keep venting carbon dioxide into the atmosphere, the way they always have, except now there's no rain-soaked rock anywhere to pull that gas back out. Picture a boiler with a pressure valve that's frozen shut while the fire underneath keeps burning exactly as before. The pressure has nowhere to go, it just keeps climbing. Millions of years pass. The carbon dioxide keeps building, trapped in the air above an ice-sealed world, with the one mechanism that would normally clear it away completely offline. And carbon dioxide is a greenhouse gas. It traps heat. Enough of it, accumulated over long enough, eventually overwhelms even a planet wrapped in reflective ice, and the freeze doesn't just end. It reverses catastrophically into a hothouse fast. Kirschvink proposed this in 1992 as an idea. It was compelling. It was also at that point still mostly a story that fit the rocks, not proof. What science needed was a single site, a single unbroken slice of rock that showed the whole transition happening in one place, so abruptly that there could be no argument about what had happened. That's what took Paul Hoffman to Namibia. By the mid-1990s, Paul Hoffman had spent years working in the deserts of Namibia, mapping rock formations that record an extraordinary span of deep time, a stretch of Earth's history called the Cryogenian, running roughly from 720 to 635 million years ago. He wasn't a stranger to these rocks, but what he was looking for, specifically, was the seam, the one place where you could put your hand on ice age debris and warm ocean rock at the same time with nothing between them, and read the story of a planet's climate flipping in what looked like an instant. He found it. Picture the scene the way the book describes it. A hillside in the Namibian desert, sun beating down on exposed rock that has sat undisturbed for well over 500 million years. Hoffman runs his hand along the face and feels the transition under his palm before his eyes have even fully processed it. Below, diamictite, the chaotic, unsorted jumble of pebbles and grit and boulders that only forms when a glacier drags material across the landscape and drops it as it melts. Directly above, touching it, is a layer of carbonate rock, the kind of pale, fine-grained stone that only precipitates out of warm, shallow, tropical seawater, the sort of rock forming today around coral reefs in the Bahamas. No gradual transition, no thousands of feet of intermediate rock recording a slow climb out of the ice, glacier, then instantly tropical ocean. Geologists call this kind of rock a cap carbonate because it sits like a lid directly on top of the glacial debris. And where it appears abruptly, everywhere Hoffman looked, all over the world, always in that exact order. Ice, then suddenly, warm sea. Here's what that means, and I want you to really picture it, because this is the moment the mystery stops being theoretical. If the planet had only glaciated locally, or seasonally, or gradually, the way an ice age works today, advancing and retreating over thousands of years, you would expect a slow, layered transition in the rock. Sediment recording a planet inching its way back toward warmth, one careful step at a time. That is not what Hoffman found. He found a cliff edge, a world that was, by every reading of that rock face, entombed in ice, and then, in what geologically amounts to almost no time at all, sitting under a warm tropical sea. Something didn't ease this planet out of the freeze. Something threw a switch. Hoffman and 3 colleagues, Kaufman, Halvorsen, and Schrag, published the case in 1998, and it did more than describe the rock. It carried the fingerprint of Kirchvink's volcano idea written directly into the chemistry. Buried in that same cap carbonate is a signature geologists read through carbon isotopes, subtly different versions of carbon atoms whose ratio in ocean rock tracks how much life was thriving in the sea. At the time, life draws down one kind of carbon faster than the other, so a healthy photosynthesizing ocean leaves one signature and a nearly dead one leaves another. Right at that seam, the signature collapses hard and fast, exactly the way you'd expect from an ocean that had spent millions of years sealed away from sunlight, its usual chemistry stalled out under an ice-locked sky. And then, sitting right above that collapse, is the rock a hothouse world would leave behind, deposited fast, laid down by a climate correction so violent it left a permanent global scar in the geologic record, a wound that closed all at once and then scarred over where it closed. This is the case Hoffman built his career on defending. Global glaciation ended abruptly by a volcanic carbon dioxide buildup that finally overwhelmed even a planet armored in ice, a hard, complete snowball Earth, equator to pole, no exceptions. It made him famous. It also, almost immediately, made him a target. Because here's the problem, and it's a real one, not a minor technicality. If Earth really did freeze completely, ocean included, all the way to the equator, under kilometers of ice for tens of millions of years, how did anything survive to tell the tale? You are, at this very moment, made of cells descended unbroken from organisms that were alive before, during, and after this event. Photosynthetic life, the ancestors of the very organisms that, billions of generations later, would become the plants and plankton. This planet's entire food web depends on, needs sunlight, not filtered starlight, actual meaningful sunlight hitting liquid water in quantities sufficient to keep metabolism running for tens of millions of years without a single break long enough to end the lineage for good. If the ocean was sealed under a solid lid of ice from pole to pole, where did that light get in? A completely frozen ocean, opaque under kilometers of ice, is about as hostile an environment for photosynthesis as this planet has ever produced. and yet the fossil and chemical record afterward shows life not just surviving the cryogenian, but apparently thriving in its aftermath, setting the stage for what some researchers have proposed, cautiously, and this part is very much a hypothesis, not an established fact, might have been the opening act for the rise of complex multicellular life not long after. So in the year 2000, a team of researchers, Hyde, Crowley, Baum, and Peltier, built a coupled climate model to test Hoffman's hard freeze scenario against the physics as carefully as anyone had yet attempted. And their model didn't reproduce a fully frozen planet. It produced something messier, and in a way, stranger, a slush ball. Thick ice at the poles and across much of the mid-latitudes, yes, but a band of open or thin ice near the equator, where the sun still hit real, if isolated, liquid water. This is the fight that has genuinely never fully resolved, and I think it's worth sitting in the discomfort of that for a moment rather than rushing past it, because it's rare that a mystery this large stays this open for this long. On one side, the abrupt, violent geochemical signature in Hoffman's Namibian rocks, which reads far more naturally as a hard, complete freeze than a partial one. On the other, the simple, stubborn fact that you are here, reading this, made of cells whose ancestors needed open water and sunlight to survive whatever this planet did to itself, and a slush ball gives them a door that a hard snowball does not. Two investigators, looking at the same crime scene, disagreeing about something as basic as whether the door was locked or merely closed. Let me give you a sense of the scale of what we're actually disagreeing about, because it's not one event. It's at least two, and they're not the same length. The rocks show two major glacial episodes within the cryogenian, separated by a warmer interval. The first, called the Sturdian, ran from roughly 717 to 6061 million years ago, around 56 million years, more or less continuously encased in ice. The second, the Marinoan, ran later, from roughly 639 to 635 million years ago. And recent work, a study published in 2025, suggests it may have lasted as briefly as around 4 million years, a comparative blink next to its predecessor. Even 4 million years, though, hold that in your head for a second the way the book asks you to. Count 1 year for every second, and 4 million years wouldn't finish playing out in your lifetime. 56 million years wouldn't finish if entire civilizations counted in relay for generation after generation. That is how long a sealed, ice-locked ocean may have sat there, chemistry stalled, volcanoes still quietly filling the sky above it with gas that had nowhere else to go. So what actually triggered the freeze in the first place? Here the evidence points cautiously toward a specific culprit. Around 718 to 720 million years ago, a massive outpouring of volcanic rock, what geologists call a large igneous province, in this case named the Franklin, erupted across what was then the supercontinent Rodinia, right as that supercontinent was beginning to break apart. Fresh volcanic basalt, still hot from eruption, happened to be sitting largely in the tropics, and fresh basalt in a warm, wet tropical climate weathers unusually fast, pulling carbon dioxide out of the air at an accelerated clip right as it's needed least. Layer onto that one more piece and hold it loosely, because it isn't a number anyone can state with total precision. The sun itself, in this era, was fainter than it is today. Stars like ours brighten slowly over billions of years, and 717 million years ago, most estimates put the sun at somewhere in the range of 5 to 7% dimmer than it shines now. Not a headline number by itself, but layered onto a supercontinent breaking apart, dumping freshly exposed rock into the tropics right as it started pulling carbon dioxide out of the sky faster than usual. A slightly fainter sun may have been the difference between a cold snap and a threshold crossed, the ice albedo mirror catching hold and beginning to grow. And once it started growing, Boudicca's math from 1969 says what happens next isn't gradual. It's a mirror getting bigger every time it reflects more light. Nothing in that feedback, on its own, tells it when to stop. Here's where I want you to actually stop and feel the size of what almost happened, because I don't think it gets said often enough this plainly. The same feedback loop that may have driven this planet into a frozen state that could have lasted indefinitely is not some exotic one-time relic of the deep past. It is running today, on your planet, in your lifetime, just in reverse. Arctic sea ice reflects sunlight back to space, the same as cryogenian ice once did. As that ice thins and retreats, darker ocean water is exposed underneath it, and that darker water absorbs more heat than the ice it replaced, which melts more ice, which exposes more dark water. Same mirror, same equation Boudico wrote down in 1969. Except now the mirror is shrinking instead of growing, and it's shrinking within your own lifetime, not across 56 million years of deep time. You are watching, in accelerated and reversed form, a live demonstration of the exact physical process that a rock face in Namibia recorded happening in the opposite direction the better part of 1 billion years ago. That symmetry is not a coincidence of physics being simple. It's the same feedback loop, expressed at planetary scale, indifferent to which direction it happens to be running. And it's worth sitting with the fact that the mechanism which may have once locked this planet into an ice age with no built-in exit is at this moment unlocking the opposite state, and nobody fully knows where that one stops either. But let's go back to the frozen ocean itself, because there's a detail in the evidence that I think is one of the strangest and most quietly moving parts of this whole story, and it's the detail that keeps the door open, even for people who favor Hoffman's hard freeze picture. If the ocean really was sealed, pole to pole, for tens of millions of years, life needed somewhere to wait it out. Not thrive, wait. A lifeboat on a planet-sized shipwreck, and the candidates researchers have proposed for where that lifeboat might have been are strange enough that they're worth picturing directly. Cracks in sea ice, kept open by geothermal heat rising from below or by the churn of ocean currents underneath. Volcanic hot springs poking up through the ice at a handful of points around the globe, tiny islands of warmth in an otherwise frozen shell. Even, some researchers have proposed, thin patches within the ice itself, dust and grit blown onto the surface, dark enough to absorb just enough sunlight to melt a shallow, sheltered pocket of liquid water a short distance down, a phenomenon that still happens on glaciers today, where scientists call these small melt pockets cryoconite holes. None of these refugia, if they existed, would have been comfortable. They would have been marginal, flickering, unstable footholds, exactly the kind of narrow survival bottleneck that, over enough millions of years, either erases a lineage completely or, if it doesn't, leaves behind organisms that have been put through a filter almost nothing else in the planet's history has matched. This is the part of Hoffman's story that even his critics find themselves circling back to, whether they accept the hard snowball or not. Something extraordinary had to survive an extraordinary bottleneck, because you are its descendant, and so is every visible living thing you have ever looked at. I mentioned earlier that this case isn't closed, and I meant it. It would be tidy to end this part of the story there. Hard freeze, hidden refugia, dramatic thaw, complex life waiting in the wings. Tidy and probably wrong to present as settled, because in 2025, a study led by a researcher named Gabrielle, published in the journal Nature, went back to the ocean chemistry recorded in cryogenian rocks and found something that doesn't sit comfortably inside the classic hard snowball picture at all. The carbon budget the chemistry implies, how much carbon was actually cycling through that ocean, and how doesn't cleanly match what a fully sealed, completely frozen ocean should have produced. It's not a rebuttal that settles the argument the other way. It's a new piece of evidence that complicates both existing pictures, hard snowball and slush ball alike, and reopens a debate that a lot of geologists had quietly assumed was mostly finished. I find that oddly comforting, in a way I didn't expect to. Not because I want the mystery to stay unsolved for its own sake, but because it's a reminder of something this whole story keeps circling back to. Even the driest, most settled-looking scientific consensus is often one well-placed rock sample away from being reopened. Hoffman thought he'd found the answer in 1998. Hyde and Peltier thought their model had corrected it in 2000. And in 2025, an ocean chemistry study came along and quietly reminded everyone that the case was never actually closed to begin with. Let that sink in for a second, because I think it's easy to hear scientists don't fully agree on this as a kind of failure, evidence that nobody really knows anything. I don't think that's what it is here. I think what you're actually looking at is one of the harder, messier crime scenes in the history of this planet. A scene where the culprit is confirmed real, the general method is understood, and the exact details of how far it went and how it ended are still being argued over by people staring at the same handful of rock faces, because the rock faces themselves are still ambiguous enough to support more than one honest reading. There's something almost humbling in that. This planet did something to itself, roughly 700 million years ago, severe enough to leave a scar visible on nearly every continent, and we still don't know, with certainty, whether it was total or partial. We know the mechanism. We know broadly the trigger. We know with genuine confidence how it likely ended. What we don't know is just how close the whole experiment came to going all the way to a planet with no door left open anywhere for anything to wait it out. Now, here's the thing I keep turning over, the part of this story that stopped being about rocks and started being about something closer to home. The ice albedo feedback isn't a quirk that only applies to planets. It's not even really a quirk of climate specifically. It's a pattern that shows up anywhere. A system's response to a change points in the same direction as the change itself, anywhere feedback reinforces rather than corrects. You felt a small personal version of this yourself, probably more than once, and never had a name for it. A bad mood that makes you withdraw from people, which makes you lonelier, which deepens the bad mood. A small debt that accrues interest, which makes it harder to pay down, which lets it accrue more interest. A rumor that spreads faster the more people repeat it, which puts it in front of more people to repeat. None of these are ice, none of these involve sunlight or latitude, but structurally, they're the identical shape, a loop that amplifies itself with no built-in mechanism guaranteeing it stops before it becomes something much larger than where it started. Earth, 717 million years ago, may have discovered that this kind of loop, run at planetary scale, doesn't politely stop itself just because stopping would be convenient for the things living on the surface. Convenience isn't a term in the equation. Only the feedback is. And that, I think, is the real weight sitting underneath this whole story, heavier, honestly, than the ice itself. We tend to assume that our own existence is evidence the system is fundamentally safe, that a planet capable of producing something as intricate as a human nervous system must, on some level, be a gentle place, tuned for survival. But that gets the story backwards. You don't exist because this planet is gentle. You may exist because a catastrophic feedback loop got interrupted, almost by accident, by volcanoes that happened to keep breathing under an ice sheet that should have shut everything down. Think about what that actually implies about the shape of the last 700 million years. A world locks itself into ice for tens of millions of years, deep enough and long enough that photosynthetic life, the base of nearly everything that would ever live afterward, is pushed down into a scattering of hidden refuges, waiting in cracks and hot springs and dust-darkened melt pockets, holding on by threads thin enough that a slightly different roll of the dice snuffs them out entirely. Then, just as improbably, a slow accumulation of volcanic gas with nowhere to go builds and builds under that ice for millions of years until it finally overwhelms even a planet wrapped in reflective white, and the whole system swings hard and fast into the opposite extreme, a hothouse violent enough to leave a permanent scar in the rock. And somewhere inside that whiplash, in the aftermath, something changed. Not immediately, not simply. And this next part is honestly the most speculative thread in this whole account. Some researchers, including Hoffman himself, have proposed that the extreme pressure of surviving that bottleneck, followed by the sudden nutrient-rich chaos of the hothouse thaw, may have helped set the stage for the rise of complex multicellular life not long afterward. I want to be honest with you that this particular idea is a hypothesis, not an established fact. An intriguing narrative reading of the timeline, not a proven mechanism, and plenty of researchers would tell you the case for it is suggestive at best. But even setting that speculative thread aside entirely, one thing about the timing is not in dispute. Not long after the cryogenian ice finally released its grip on this planet, the fossil record starts showing something it had never shown before. More complexity, more kinds of life, doing more different things than in the preceding several billion years combined. Whether the ice caused that or merely came right before it by coincidence is genuinely unresolved. But I think either answer is strange enough to sit with. Either this planet had to nearly kill everything twice in order for something like you to eventually become possible, or the two events sit side by side in deep time as an almost unbearable coincidence, a planet that nearly froze itself into permanent silence, followed shortly after, geologically speaking, by the moment everything got interesting. Here's the part I actually think about most, more than the ice itself, more than the volcanoes, more than the 30-year argument between hard snowball and slush ball. It's this: the equations that describe how a planet's ice can spiral out of control were sitting there, true, the whole time, decades before anyone found the rock in Namibia that proved they'd once actually been triggered. The physics didn't wait for someone to notice it. It was already real. It had already happened, once, in a version severe enough to leave a mark that would still be legible 600 million years later to a person crouched on a hillside with a rock hammer. That's the uncomfortable thing about a feedback loop with no built-in reverse gear. It doesn't care whether anyone is watching or whether anyone has modeled it yet, or whether the consequences would be catastrophic for everything alive at the time. It just runs the moment the conditions line up, exactly the way gravity pulls a dropped object down, whether or not you've done the math on how fast it will fall. And you are, this very moment, standing on top of a planet where that switch has been thrown before. Not hypothetically, not as a thought experiment run on a computer somewhere. It happened, and the rock still remembers it happening, in a seam you could put your hand on if you flew to the right hillside in Namibia and reached out and touched it yourself. I don't say that to be alarming for its own sake. I say it because I think there's something genuinely different about understanding a danger as a live physical possibility rather than as an abstraction you've heard mentioned in passing. The ice-albedo feedback isn't a metaphor borrowed from climate science to make a point about something else. It is the literal mechanism still running today, in reverse, in the Arctic, right now, while you watch this. The same loop. The same lack of a guaranteed built-in stopping point, just pointed the other direction on a planet that is, this time, watching itself do it. I keep thinking about the phrase Hoffman's critics used against him, and that his supporters eventually turned into something more like a badge of honor. Snowball versus slushball, hard freeze versus open water, an argument over whether the door was locked or merely closed. And I keep thinking that the argument matters less in a strange way than the fact that there was a door at all, that whatever this planet did to itself 700 million years ago, it left just enough of a crack, somewhere, for something to wait it out. A cryoconite hole, a hot spring, a gap under thinning ice at the equator, if the slushball model's right. Something, somewhere, held on. You are right now breathing air that a photosynthesizing ancestor billions of generations removed from you helped make possible by surviving a bottleneck this planet may have designed almost by accident, entirely out of physics that doesn't care about outcomes one way or the other. That's not a comforting thought, exactly. But I don't think it's meant to be. I think it's meant to make you feel, for a moment, the actual size of what it took to get here. Not a gentle, welcoming planet handing life a soft place to grow, but a planet that came close enough to freezing itself into permanent silence that the evidence is still legible in stone. And something got through anyway. There's an image that keeps surfacing for me every time I try to picture the sealed ocean itself, rather than just the ice sitting on top of it. And it's this: a terrarium, sealed shut, left running on a shelf for 60 million years. Not the neat kind you might have kept as a kid, glass walls and a single healthy fern. A terrarium the size of an ocean, its usual exchange with the sky cut off entirely, its internal chemistry left to do whatever internal chemistry does when nothing from outside can get in or out. And what happens inside a sealed system when the only thing still adding energy to it is a slow, steady trickle of gas from below, with the normal exit welded shut? It builds. Not dramatically, not all at once, a room filling with gas through a single door that's been sealed closed, filling so gradually that for most of the tens of millions of years in question, nothing about the surface world would have looked like it was building toward anything at all. Just ice. just quiet. Just volcanoes, doing what volcanoes always do, filling a room with no ventilation. That's what makes the weathering thermostat's shutdown so unnerving to me, more than the ice itself. It's not that the mechanism failed loudly. It failed silently, by simply having nothing left to act on. No exposed rock, no rainfall reaching stone, no rivers carrying the products of that reaction anywhere. A thermostat that works perfectly, day after day, decade after decade, right up until the one condition arises that removes its ability to do anything at all, and then just sits there, uselessly correct in its design, while the room fills anyway. I think that's worth sitting with for a second longer, because it's such a specific kind of failure. It isn't that the physics of the thermostat was wrong. Hoffman's Namibia rocks and everyone's model since agree that the weathering feedback is real, that it does exactly what it's supposed to do under normal conditions, correcting a warming world by drawing carbon back down, correcting a cooling one by letting it build back up. The mechanism was never broken. It was just switched off by the very crisis it should have been preventing, in a loop grim enough that it's almost darkly elegant. The ice grows because there's nothing pulling carbon dioxide down fast enough, and once the ice grows far enough, the one thing that pulls carbon dioxide down at all is buried under it. Now, hold that image next to the timescale again, because I don't think it lands until you actually try to feel the length of it, rather than just hear the number. 56 million years for the Sturtian glaciation, possibly as brief as 4 million for the Marinoan, according to that 2025 estimate. Briefer, but still long enough that if you tried to walk it out one step for every year, you would be walking for the rest of your life and the rest of your children's lives and still not reach the end. For all of that time, somewhere in a scattering of cracks and hot springs and sunlit dust pockets on the surface of a nearly silent, nearly frozen planet, something kept a pulse. Not thriving, not flourishing, just not stopping. Generation after generation of some of the simplest organisms this planet has ever produced, holding a line that, if it broke even once completely, would have ended the entire experiment right there. No thaw to look forward to, no hothouse on the other side, because there would have been nothing left for the thaw to reach. I don't think there's a tidier way to say what that actually is than this. For tens of millions of years, the continued existence of every visible form of life that would ever exist on this planet afterward depended on something that small, holding on in a place that precarious for that unimaginably long. Not a single dramatic stand. An endurance test with no finish line in sight, run by organisms that had no way of knowing there was an ending coming at all. And when the ending did come, it wasn't gentle either. Whatever geochemical evidence Hoffman found in that cap carbonate, laid down directly above the glacial debris with no gap between them, reads as fast and violent by geological standards, a climate correction so sudden it left a permanent global signature in stone. A slow-building crisis, ending in what may have been one of the more abrupt climate reversals this planet has ever undergone. From a state so cold it should, by Boutiquot's own equations, have had no way back, to a hothouse in what geologically amounts to almost no time at all. Whatever survived the ice then had to survive that too. The fight I mentioned earlier, back when I first named this book, the one that followed Hoffman for the rest of his career, is worth actually telling as its own scene, because it wasn't polite, and it wasn't quick. Hoffman published his case in 1998, expecting it to land as a solved mystery, a satisfying answer to a paradox that had been sitting unresolved since Harland first laid it out back in 1964. Instead, it landed as a provocation. Other geologists and climate modelers working through the biological problem I already walked you through. The simple, stubborn fact of photosynthetic life needing open water and real sunlight to survive, pushed back hard and pushed back publicly. Some of that pushback was collegial, the ordinary friction of science working as it's supposed to. Some of it, by the book's account, got personal in the way scientific disputes sometimes do when a career has been staked on one particular reading of the evidence. Hoffman didn't back down. For decades afterward, he continued defending the hard freeze interpretation, continued returning to Namibia, continued arguing his case against slushball advocates like the Hyde and Peltier team, and against the growing chorus of biologists asking, reasonably, how anything could have survived a completely sealed ocean for tens of millions of years. It became, by most accounts, one of the defining arguments of his professional life, not a quiet academic footnote, but a real, sustained fight over how to read a single seam of rock in the desert. I bring this up not for the drama of it, though there's plenty there, but because I think it says something true about how science like this actually gets made. It isn't a single triumphant discovery, cleanly verified and then universally accepted. It's a claim thrown into a room full of skeptical, careful people who have every professional incentive to find the hole in it, and then decades of argument, refinement, and new evidence, some of it, like that 2025 ocean chemistry study, arriving long after most people assumed the debate had quieted down. Hoffman may turn out to have been broadly right. He may turn out to have been broadly wrong. What's not in question is that he forced an entire field to take Mawson's half-century-old, half-forgotten claim seriously again, and that the argument he started is, as of the most recent research, still not finished. There's a version of this story that would end with a clean answer: hard snowball confirmed or slushball confirmed, case closed, next mystery. That's not the version the evidence has actually given us, and I think pretending otherwise would be a disservice to how genuinely strange and unresolved this piece of the planet's past still is. Here's what I keep coming back to. Underneath all of it, your own body carries a quieter echo of this story than you might expect, and it has nothing to do with ice at all. Every cell in your body that generates energy does it using structures called mitochondria, the descendants, many scientists believe, of free-living microorganisms that were absorbed into larger cells billions of years ago and never left. That absorption happened long before the cryogenian. But the lineage that eventually became those cells, the one running quietly inside every one of your own cells right now, is the same unbroken thread that had to pass through whatever bottleneck the snowball Earth actually was, a hard freeze or slushball, refugia in a hot spring, or refugia in an equatorial gap of open water. It doesn't matter for this purpose which version turns out to be correct. Either way, the thread held. It had to. Your evidence that it did, running on the exact same feedback loop physics that, at a planetary scale, once came close enough to erasing it that the argument over how close is still ongoing, 600 and some million years later, in journals being published this year. There's one more honest thing worth saying. Plainly, once before I let this rest, because I don't want to leave you with a tidier picture of the science than what actually exists. What's genuinely settled: low-latitude glacial deposits are real and well documented on nearly every continent. The ice albedo feedback and the weathering thermostat are both real, provable mechanisms, not speculation. The Namibian cap carbonates and their abrupt isotope collapse are documented rock, not interpretation. What's still contested, honestly and actively, as of the most recent research, whether the freeze was total or partial and exactly how the trigger sequence played out. What's interpretation, dressed up as narrative rather than proof? The idea that this bottleneck directly caused the rise of complex life afterward. It's a compelling reading of a timeline. It is not an established mechanism, and I don't think it does the story justice to pretend otherwise. What is certain is this: a planet-sized feedback loop built on nothing more exotic than the color of ice and the color of open water ran once at full scale for tens of millions of years, with no guarantee written into the physics that it would ever stop on its own. It stopped anyway, not because anything alive intervened, not because the system corrected itself the way the comfortable version of this story likes to assume climate always does, but because volcanoes kept doing what volcanoes do, underneath a lid that couldn't hold forever. There's one earlier thread I skipped past quickly that deserves its own moment, because it's the piece that explains why this particular era, out of all the eras in this planet's 4.5 billion year history, was the one where the ice albedo mirror actually caught. Geologists dating the volcanic rock associated with that Franklin eruption place hit it roughly 718 to 720 million years ago, right at the edge of and just before the Sturtian glaciation begins in the rock record. That's not a loose coincidence researchers are reading too much into. It's a precise enough match in timing that it reads as cause and effect. A supercontinent called Rodinia tearing itself apart, spilling fresh volcanic basalt across a stretch of crust that happened by the accident of continental drift to be sitting largely in the tropics at that exact moment. And fresh basalt is chemically eager. It hasn't had time to develop the weathered outer crust that slows a rock's reactions down over millions of years of exposure. It's raw, and in a warm, wet, tropical climate, raw basalt pulls carbon dioxide out of the air and locks it into new minerals unusually fast. So picture the sequence, laid end to end, the way the rock seems to argue it happened. A supercontinent breaks apart, fresh volcanic rock spills into the tropics, right where rainfall is heaviest and weathering runs fastest under normal circumstances. That rock starts drawing carbon dioxide out of the sky faster than the volcano's venting it can keep the balance level. The sun, meanwhile, is dimmer than it is today, not by some large, precisely known figure, but by an amount most estimates place somewhere around 5 to 7%, faint enough that the margin this planet had to work with before the ice albedo mirror caught and started feeding itself was thinner than it would be if the same sequence of events happened today. Carbon dioxide drops, the planet cools, ice creeps down past the line Boudicco's equations warned about, and the mirror stops being a self-correcting curiosity and starts being a runaway. None of this is a single smoking gun. It's several independent lines of evidence: the dated volcanic rock, the reconstructed position of the continents, the physics of weathering, the astrophysics of a young sun, converging on the same narrow window of time, closely enough that most researchers treat it as the leading account of the trigger, even while allowing that the exact sequencing is still, like so much else in this story, not fully nailed down. What strikes me most about that convergence is how ordinary every individual piece of it is. A continent splitting apart is not unusual. Continents have split apart many times across this planet's history, before and since, without triggering a runaway freeze. A slightly fainter young sun is just where every star like ours happens to sit early in its life. Nothing anomalous about it at all. Rain falling on fresh volcanic rock happens constantly, all over this planet right now, without incident. It was the layering, several unremarkable individually survivable conditions, arriving in the same narrow window, tipping a threshold that, once crossed, had no mechanism written into it to uncross itself. That, more than anything else in this story, is the detail I find hardest to shake. Catastrophe on this scale didn't need anything exotic. It needed ordinary conditions, stacked in the wrong order, meeting a feedback loop patient enough to wait for exactly that alignment. Take a breath, let it out slowly, and notice that you didn't have to think about it. Notice that the air moved and your chest fell, and nothing had to build up for 60 million years with nowhere to go. That's the part I keep returning to. Not the ice, the door. Somewhere, in a crack in a glacier or a hot spring pushing up through a frozen sea or a thin patch of sunlit dust, something held on long enough for this moment to become possible, the one where you're sitting somewhere, breathing freely, turning over a story about a planet that once came close enough to sealing itself shut forever that geologists are still arguing, this year, about exactly how close. I don't know if the door was wide open or barely a crack. Nobody does yet. But it was there. And the switch that closed it, the one written into that same simple, patient equation about ice and light and mirrors, is still sitting in the physics of this planet, indifferent to outcomes, waiting for the next alignment of ordinary things in the wrong order. For now, though, the ice is only a memory kept in a rock in Namibia. The air moves. The door stays open. Take another breath. Feel it. That's the whole story, really, held in a single, unremarkable, uninterrupted breath.